for today's lecture. So let's just recall where we left off last week. We looked at a construction of a public key encryption scheme that's based on trapdoor permutations. And we used this trapdoor permutation, and we also used a hardcore predicate for this trapdoor permutation. So something, hardcore predicate, a bit or a predicate on X that you cannot predict if you just know the value of X under the hardcore, under the trapdoor permutation. Okay? And our encryption scheme was only defined for messages of length 1. So we were only able to encrypt a single bit. And that was because our key generation algorithm was just a key generation algorithm of the trapdoor permutation. So the instance parameters are just the public key of the encryption scheme. The trapdoor is a secret key. And the encryption now of a single bit works as follows. We sample an X using from the instance that's defined by the public key. And then we output the ciphertext as we apply the trapdoor permutation to X. And then the second component is MX, or the hardcore predicate of X given the instance. Okay, and here, since the hardcore predicate is a single bit, this is only allowed to be a single bit. Yeah? And the decryption, you do the obvious thing. If you have the trapdoor or the secret key, you can invert compute X back from this thing here, and then you can just compute the hardcore predicate and XOR it to the second component of your ciphertext, as stated here. Okay, but this is, as I said, just so we needed this hardcore only for 1 bit. This is encryption only for 1 bit because we work with a hardcore predicate. So this construction only works for single bit messages, and also we saw in the proof that we used this property, or the fact that we only work on single bits. We used this funny thing where we complemented one and then we could complement the other part in the XOR equivalently. Okay. One can somewhat modify this where we not just use hardcore predicates but hardcore strings. So substrings of an output that of an X that's hard to predict given only the trapdoor permutation value on X. But that still is not very efficient. Obviously we want to extend this scheme to something that works for messages that are longer than just a single bit. Single bit encryption is not very helpful, but we already know that if we have a scheme that's CPA secure, and we have indistinguishable encryptions, then we have multiple indistinguishable encryptions. So we just can encrypt longer messages by encrypting the bits in the message individually. And this is exactly what we did in this first approach that I want to discuss. So we have that the key generation is as in our construction. So we use a trapdoor permutation. The instance parameters are the public key. The trapdoor is a secret key. And then if we want to encrypt a message consisting of a certain number of bits, what we do is for each bit in the message, we pick an xi using the sampling algorithm, and then we encrypt the corresponding bit mi using exactly this xi. So we have for x, we pick this x1, we compute fi of x1, we XOR the hardcore predicate at x1 with m1, and so on. And that's just concatenating the individual encryptions. And by our theorem that we had on multiple encryptions, this is a secure construction. It's still a wasteful construction, obviously, because if you think of a trapdoor permutation like RSA, and we want that to be secure, then these xi's are roughly around, say, 2048 or 4096 bits long. Since we have a permutation, fi of xi is also of 2048 or 4096 bits. So for each individual bit, you use roughly 2000 or 4000 bits to encrypt it. That obviously is not very nice, okay? So you have a factor of roughly several thousand expansion between ciphertext and message. And obviously it's also not very efficient to compute. It's polynomial time, yes, but for each bit you have to evaluate this trapdoor permutation. And evaluating RSA is not something, so for a single evaluation that's quite efficient. But if you have to do that millions or billions of times, then you run out of time quite fast. Let's first address the first problem, namely that this is a very wasteful scheme. And one way to get around this is the following construction. Instead of sampling for each bit a new xi, we just sample one x1. Okay? And then we set the sequence of xi's as follows. Xi plus 1 is f, the trapdoor permutation, applied to the previous element. So you have x1 is the original one, then you have x2, which is fi of x1, and then x3 is fi of x1, and so on. Okay? And what you then do in the encryption, you have R message bits. Okay? You include into the ciphertext only xl plus 1. Right? So xl plus 1 is fi evaluated xl. Okay? And then to encrypt all the bits, you XOR M1 with HCI of X1. M2 is XORed with HCI of X2, and so on. And ML is XORed with HCI of XL. Okay? To decrypt, easy. We get this element. We use the inversion algorithm to get XI. The XL, sorry, XL. Then we can compute ML. Once we have XL, we use our inversion algorithm to get XL minus 1. We get ML minus 1, and so on. So we decrypt by computing the XIs in the reverse order, starting from the last one. Okay. Now, why should this be secure? Let me give you first the intuitive argument. So it's clear that if I ignore all this here and just look at this part here, this and this is like we did in the original scheme. Notice that we have a trapdoor permutation. So if x1, say, is an element picked uniformly at random from the domain di, I apply a permutation to that element. It's still uniform. Apply yet another time the permutation and keep doing that. So I get always uniform elements. So this here is a distributed uniformly at random as in the original scheme. So this one here is certainly secure. But then what we do is, well, if, say, x1 is sampled correctly, fi of x1, it's hard to compute because it's a trapdoor permutation without having the trapdoor. So instead of using a fresh one, I use one that is hard to predict or hard to compute. That should be as good as a new one. Okay? And then I keep going. Right? If the second one is also hard to predict, then the third one should be hard to predict because applying the trapdoor permutation should not modify that. Okay. In the formal proof, you use a hybrid argument. Actually, what you do is you a hybrid between encrypting like this and then encrypting like this. So let me write down what you do in a hybrid or hybrid encryption of M1 or hybrid distribution, say dk on ciphertext. For a given message M, you would do the following. You pick x1 up to xk, and then you pick an xk plus 1. Okay. And then your distribution would be you have C1 up to CL, or let's say, no, that's not what I want. So your ciphertext now would be C would include x1 up to xk plus 1. You get all these things. Or I should, let me write it differently. So you include first fi of x1 and hci x1 XOR M1. Okay? So you encrypt the first bit basically using this method here. You do the same for the second bit. So you do fi of x2, and then you do hi of x2 XOR M2, and so on until you have fi of xk, hci of xk plus XOR mk. And then, so we still have to encrypt now L minus k many bits, right? So and from that point onwards, I use sort of this encryption scheme. So for now, I set, say, I set xk plus 1 I have defined, and then I set xk plus 2 to be fi of xk plus 1, and so on. Okay? And here I include my x L minus k plus 1, right? Because here I included one more than the number of bits I want to encrypt. This number of bits I still want to encrypt with this is L minus k many bits. And then I do what I wrote down over there. So I use hci of xk plus 1, XOR mk plus 1, and so on, until at the very end I have fi of xl, which is now really the correct index, hci of xl XOR ml. Okay? And then you can do this hybrid argument and reduce the security of this scheme to the security of the original scheme. And that works as long as the messages are polynomially long in the security parameter, but that's something we need in any case, because so we can use this kind of hybrid argument here as well. to do this, and this is obviously much more efficient, or in terms of expansion of the ciphertext, this is much better than this one. Again, recall RSA. You include one element, say, which has 2,000 or 4,000 bits, but then this has the same length as the message. So instead of multiplying by 2,000 or 4,000, you just add 2,000 or 4,000. Okay. But evaluating or computing an encryption has the same complexity here as here. Because again, for each bit you have to apply the trapdoor permutation once. That doesn't change. Okay, so expansion is okay, but efficiency, we didn't gain anything. Okay. Yeah. So therefore I want to, there are many other ways to make this, public key encryption very efficient. I want to present to you one that is uses the random oracle model, and that has also the advantage of being, under the right circumstances, being CCA secure, which I want to discuss later. And actually it's a basis for a construction that sees CCA security also without random oracles. Okay, so now we want a really efficient scheme. Again, we use a trapdoor permutation. Okay, to do that. But on top of using a trapdoor permutation, we also use a private key encryption scheme. Okay? We combine a trapdoor permutation with a private key encryption scheme. And by this calligraphic I denote the set of all instance parameters that can be generated by the trapdoor permutation, the key generation of the trapdoor permutation. And for an n and I denote by in, calligraphic in, the set of all instance parameters I that can be generated by this generation algorithm on input 1 to the n. Yeah? And first of all, I don't need actually the random oracle model, but later on in the theorem I need that certain functions are modeled as random oracles, and the functions that we are looking at come from this family calligraphic H. And for each I in the instance set, we have a function hi. And if I comes from this in, so was generated by this 1 over n, this hi maps di to 0, 1 to the n. Okay. And I also assume, which is the thing that we did anyway, but just to recall, on input 1 to the n, I assume that the key generation algorithm of pi bar outputs a key in 0, 1 to the n. We actually wrote down that it outputs a key uniformly at random in 0, 1 to the n. Okay. So the range of every hi, if it was generated by the trapdoor generation algorithm on input 1 to the n, is actually the key space of our private key encryption scheme. Yeah? And you see why I need that. Now, based on these ingredients, we can define the following construction. Oops, sorry. This should be the pi. We have the trapdoor permutation. This should be pi bar, not pi sk. I just forgot to change that. And that H be this function family that I defined on the previous slide. And now we have a public key encryption scheme as follows. The key generation algorithm is, again, the key generation algorithm of the trapdoor permutation. And I completely got my notation wrong. So this should be the key generation of the trapdoor permutation, not gen bar. Okay? So this should be, let's try to, so this should be gone, this should be this, and this should be gone, and here should be a TD. This is the right thing to do. Okay? Okay, good. So it's a key generation algorithm of the trapdoor permutation. Now to encrypt a single message, which is from 0, 1 star, I assume that the private key encryption scheme works for messages of arbitrary length. Yeah? So it can encrypt messages of arbitrary length. And what I do to encrypt, as before, I sample using the sampling algorithm of the trapdoor permutation on the instance parameter, which is the public key. I set y as fi of x. And now comes the part where we deviate from the previous constructions and make it much more efficient. We set k as hi of x. So we map, using this function ai, we map x to the key space of the private key encryption scheme, namely 0, 1 to the n. And I use that k in the encryption, namely my encryption of my message m is y plus the encryption of m using my private key encryption scheme and using this key k that I generated in this way. Okay. And the decryption, you get the input 1 to the n, you get the secret key, which is the trapdoor, and the ciphertext, which contains of two elements, y and s. Y is in DI, S is in 0, 1 star. Again, what we do is we first invert x, invert y using the trapdoor to get x. Once I have x, I can compute the key k by using hi, which I assume is public. And then we just decrypt s using the key k, and that gives us my message m. And obviously it's correct. Okay. Now the advantage of this scheme is that, okay, it only uses one element from DI, and then it has only to apply the trapdoor permutation once. It has to apply this hi once, and then it simply uses the encryption function of the private key encryption scheme, which typically is very efficient. You could think of this encryption scheme, the private key encryption scheme, for example, as a one-time pad, which is not defined on messages of arbitrary length, but except for that, that's good. Okay. So under which circumstances is this secure? So if pi d is a trapdoor permutation and this pi bar, the private key encryption scheme, has indistinguishable encryption against eavesdropping attacks, and the functions hi all are modeled as random oracles, every individual one, then this construction is even CPA secure. So we don't even need that the private key encryption scheme that we use is CPA secure. For that, really eavesdropping security is enough to get a scheme that's CPA secure. So you could really use a one-time pad if you just want to encrypt messages of a fixed length to do that. Or use our pseudorandom generator construction, for example. This would also work. Okay? So I don't want to give you the exact proof, but I want to give you an idea how one can prove this thing. Let me write down a few things on the board as well. So proof outline. Should be 10.18. So let A be a fixed but arbitrary adversary against pi as in construction. Okay. Okay. And by that C, which is y comma s, denotes the challenge ciphertext. That A eventually gets. So A has picked beforehand, as usual, the two messages M0 and M1, and then C is of the following form: it's HCI of an X, and the encryption under this key K of MB. Okay? Where X was sampled using our sampling algorithm. Oops, sorry, it's not HCI, it's Fi of X, sorry. Not the trapdoor, not the hardcore. We don't need a hardcore predicate. And K is Hi of X. Okay? Now we distinguish two cases for a successful adversary. Okay? So the adversary has access to the random oracle. Okay? So it can query the random oracle, okay, on all kinds of things. And we distinguish the following two cases. A queries the random oracle for Hi of X. Okay. And the second case is A does not query for Hi of X. Okay? Now, if we have an adversary that queries Hi of X, a query to the random oracle consists of X. Okay? But then, if it queries for X, it has found the preimage of this Y. Okay? We simply output the preimage of this X as a preimage of Y. Which means that in that case, we can turn this adversary A into an inverter for the trapdoor permutation. Yeah? Okay. Then we have the two cases. as on slide. Okay, so the first case, A can be used to construct inversely against the wideness of pi td, so we can invert. Now, if A has never queried hi of x, yeah, by our definition of random oracle, if you never queried for a value, that value is still uniform random. Okay? So if we are in case 2, this k that is used here for the adversary A looks uniform random. Okay? But then he has to decrypt correctly one of two messages that he chose himself under a uniform random key. And that obviously can then be used to construct an adversary against the eavesdropping security of pi bar of our secret key a private key encryption scheme. Yeah. Why is it eavesdropping? Well, if it never queried for this hi of x, it doesn't know k. So it cannot query the encryption oracle on k. Because if it did query the encryption oracle on k, it would have to query hi at x, which we, in this case, we excluded that. Okay. So these are the two cases, and formally we actually use a difference lemma to prove this, to make this formal. Now, the difference lemma was we had this game. In this case, it would be the original game, the CPA security game. The game 2 would be that we assume that, or that we assume that this thing was never done, right? And then we know that the difference between the games is the probability for a certain event to happen, and the probability for the event to happen is exactly that A queries for hi of x. And this probability then can be analyzed using this, the assumption that there was pi dd is one way. So it's pretty straightforward proof. Yeah. Yep. But it's important. So at least in the proof, it's important that we model this hi as a random oracle, because otherwise we cannot argue that if this is not, if case 1 does not occur, then this key k is completely hidden, in the sense that it's still uniform from everything that A sees, uniform and independent from everything that A sees. Yep. Good. So the difference lemma is lemma 5.4, and we used it to analyze the security of authenticated encryption schemes. This encrypt then authenticate. Okay. Yeah. But it turns out that this construction is even nicer. It has even nicer properties. And to analyze this, I've skipped this hybrid encryption part. We'll come back to it later in the second part. And I want to talk about chosen ciphertext security of public key encryption schemes. Okay. We already defined chosen ciphertext security for private key encryption schemes, and we use basically the same games to define chosen ciphertext security for public key encryption schemes, except as usual in the public key encryption schemes we don't use encryption oracles, because the adversary gets the public key anyway and he can encrypt himself. But as in the private key setting, also for public key, the chosen ciphertext security is the security model that we generally want to achieve. Sometimes if we use public key encryption scheme as ingredients for other constructions, we can get away with something that's weaker, but as a standalone primitive, we usually want to achieve chosen ciphertext security. So here is a game to define this chosen ciphertext security. It's called the chosen ciphertext indistinguishability game. And we start out with a public key encryption scheme pi. And the game, as usual, is between a challenger and an adversary against pi. And on input 1 to the n, the game proceeds as follows. First, the challenger chooses a secret key public key pair using the key generation algorithm of the public key encryption scheme under consideration. And it gives pk to A. Then A asks C for decryptions of adaptively chosen ciphertext C1 and so on. And obviously can also compute encryptions of messages on its own because it has a plain text, but it, for the decryption, since it does not have the secret key, it uses the challenger. And eventually, A outputs two messages, M0, M1, where, as usual, we require that the two messages have the same length. C, as usual, chooses a bit B in 0, 1 and computes the encryption of C under C as the encryption of MB under the public key PK, and it gives C to A. A asks, as in step 2, for decryptions, but it is not allowed to query the decryption of C. And clearly. And A outputs a bit B prime. And the result of the game is 1 if and only if B is equal to B prime. So that's similar to what we had in the private key setting, except that we don't have these the encryption queries. We don't need them for the adversary because he has a public key. And then we have our usual steps. We write pub cca a pi of n for the output of the game on input 1 to the n. It's a random variable. The random choices over here, the random choices made here, the random choices that A makes here, the random choice of B, and the random choices used in the encryption, and then the random choices that A does here. It's a PPT. So overall, these random choices, this is a random variable that denotes this output, and we denote the CCA advantage of A against pi on input 1 to the n as a probability that it succeeds, namely that it outputs, guesses the right bit, minus 1/2. As usual, we subtract 1/2 because you can always guess correctly with 1/2 if we want to know how much better you are than just guessing. And we take the absolute value. We've discussed this absolute value before. Yeah. And then we call a public key encryption scheme pi, or say that it has indistinguishable encryptions under chosen ciphertext attacks, or is simply CCA secure, if for every probabilistic polynomial time adversary A there is a negligible function mu such that the CCA advantage is on n is bounded by mu of n, or is mu of n. No, this CCA advantage is a negligible function. Okay? So let's go back to our encryption schemes that we have seen so far, namely these here, or let's start actually with this here. Where it is, here. And let's check, is this thing, we proved that it's CPA secure. Is it CCA secure? Any ideas? Don't write this down, because it's sort of the question. Is it CCA secure? Is it not CCA secure? Is it CCA secure under certain assumptions? What happens? Hint, you can ask for any the decryption of any ciphertext except the one that you get at this, as a challenge ciphertext. Yeah.
Maybe if we get the challenge ciphertext C, we could probably just flip the bit in the second component and then obtain a decryption of it. And then if we have the decryption, we have to flip the bit again and have the original or the decryption of the original message.
Exactly. So it's not CCA secure under no circumstances. This is basically the same idea as the one that we used to show that the pseudo-random function construction in the private key setting is not secure, is not CCA secure, although it is CPA secure under the assumption that we have a pseudo-random function. So why not? So A chooses simply M0 to be 0, M1 to be 1. Yeah? Upon receiving C, which is Y, S, A asks for decryption of C bar, which is, we keep this here, but we flip the second component. So we XOR 1. Yeah? And then, and outputs so if it receives message M bar or M bar. It outputs B as M bar XOR 1. It flips the output as well. That's exactly what you said, right? So this is again in 0, 1. And this A succeeds with probability 1. Why does it do that? Well, you can just push the XOR 1 into M XOR 1. So you flip the message that you encrypt, but keep this HI of X in the first component. And then you just flip back when you get the message. And the way I choose it, the M0 is 0, M1 is 1. That's why this is the right bit. Okay. Without loss of, no, I just do that. Okay. So this is not CCA secure because you can modify ciphertext into meaningful other ciphertext that give you information about the original, the decryption of the original ciphertext. Okay. We call this property often malleability. Ciphertexts here in the scheme are malleable. You can modify them. You can massage them into something, in a controlled way into something else. Okay. We saw this quite often. We not only saw this in the pseudo-random function construction, we also saw that with one-time pad that we can do that. There it's not CPA secure and whatever. So malleability, if you are malleable, you cannot be CCA secure. Okay. Under certain circumstances, the converse is also true. Okay, so this is not CCA secure. And hence, this is not CCA secure. This is not CCA secure. And if you go to this here, to this construction here, we'll discuss it later. Okay? But it's clearly sort of, if this guy here, the encryption here, if that is not CCA secure, if there's something malleable that you can modify encryptions, then you can basically, but a slightly more complicated way, using the way you can transform these things, you can attack this scheme. So it's clearly that this, if it's just eavesdropping secure, that should also not be CCA secure. Okay, but maybe we can strengthen it. Okay, but before that, I want to discuss a few other things. So CCA security for public key encryption scheme is much harder to achieve than for private key encryption scheme. In particular, if you want to do that in the so-called standard model. You don't want to use random oracles. If you really want to do it without using random oracles. But there are known general constructions, and these use quite complicated things. One thing that in some lecture eventually I will explain this. It's based on so-called adaptive, non-interactive, zero-knowledge proofs of knowledge. You can imagine that explaining this thing here takes some time because You have to explain zero knowledge, proofs of knowledge. You have to interpret non-interactive, and you have to do what is meant by adaptive. And they need to have special properties, so-called one-time simulation soundness. So I don't want to go into these things, but these things exist, and they can be constructed from trapdoor permutations. And that's important. That's something I will state later. You can also use so-called smooth hash-proof systems, which are universal one-way hash functions families that have additional properties, okay? That I don't want to go into details. A third way to construct these things is based on based on identity-based encryption. Identity-based encryption is a special public key encryption schemes where every bit string can serve as a public key, which is very different from what we've seen. Like RSA, not every bit string is a legitimate RSA public key, because you will not be able to partition it into a part N and E, where N is a product of two primes. Most bit strings do not correspond to these things. But there are encryption schemes for which every bit string can be a public key, and the corresponding secret key can be evaluated using a so-called master secret key. These things are quite new. The first construction goes back to 2001. This construction goes back to the 1990s somewhere, and this here goes back to 1998 roughly. This year, the smooth hash-proof systems, that was used actually in 1998 by Ronald Kramer and Victor Schub to construct the first practical CCA, secure and public key encryption scheme. And in fact, they first had a construction that used an extension of Al-Jamal. Al-Jamal in itself is not CCA secure, but they were able to extend it in such a way that it gives you something that's CCA secure, and then they abstracted from this construction all the properties that they really need, and then they came up with smooth hash-proof systems. This is sort of practical, but still not really, really practical. So this is what I just said. And as I said, if trapdoor permutations exist, then CCA secure public key encryption schemes, because we can construct these non-interactive zero-knowledge proofs of knowledge. Okay? In public, this is what we use is something that's usually called the optimal asymmetric encryption padding, OAEP, is used. And for example, in PKCS version number 1, version 2.0, that is used actually. This is an improvement on this version 1.0, which actually was thought to be CCA secure, but then turned out it wasn't. First, it was discovered by a real practical attack by Daniel Bleichenbacher, and then people had to go back to the proofs to find where they went wrong. And they found the missing parts, or the wrong parts, and then they fixed them, and then they could do this. Combination of RSA and this optimal asymmetric encryption padding leads to a CCA secure public key encryption scheme, but this is can only be shown to be secure in the random oracle model. This usually. And actually this is basically what we have here. Another technique to obtain CCA secure encryption schemes in the random oracle model is the so-called Fujisako-Okamoto transformation. And that's basically a modified, extended, generalized, and complicated version of what I will describe next. Okay. And I will tell you why it's more general. But we already know a CCA secure public key encryption scheme because our construction 10.17 can actually be shown to be CCA secure if you not only assume that pi is a trapdoor permutation, but also that the private key encryption scheme is CCA secure. Okay. So go back, if we go back to, this way to our construction, which is here. When we discussed it over there, if this thing here is not CCA secure, you can basically modify it, this thing here, to get a meaningful encryption of some cipher, some message, and then you could use that to decrypt, to win the CCA game. Right? What this theorem that I just presented says that if this here is CCA secure, you get something that's CCA secure overall. Okay. The way you prove that is very similar to what I wrote down on the board previously about the proof outline. Namely, what you can do here as well is, again, we look at the challenge ciphertext, where this S is this encryption, K is this key again, and Y is this Fi of X. That's as before. Yeah. And again, we can distinguish these two cases. Okay? Queries on the random oracle for Hi of X for this particular X here that's used in the challenge ciphertext, or it does not do that. The first case you can analyze as before. Then you break the one-wayness of the trapdoor permutation. So that cannot happen, or happens only with negligible probability. If we do not query the random oracle for Hi of X, then you can transform A to construct an adversary against the CCA security of pi bar. And that part here, in the CPA part, this is actually quite easy to show that this is then CPA secure. CCA security here of pi bar, you have to be a little bit more careful. And what you do is you really need to basically use the same proof technique, but you also, when you answer hash queries or random oracle queries, you have to do it cleverly. And basically, on a certain level of abstraction, you do something similar to what we did in the proof of theorem 8.5, where we proved the security of the RSA full domain hash. And remember, maybe what we did there is we answered the random oracle queries very cleverly, namely in such a way that then we could answer. They were uniform random, but sort of we had side information that was allowing us to then answer signature queries, which we have to answer in the forgery game. Here, we will answer these hash queries, random oracle queries. Again, it's the right distribution, uniform at random, but sort of in a clever way, such that we will be able to answer decryption queries without knowing the secret key. without knowing the trapdoor. And that's important because otherwise we cannot play the challenger for an adversary against the CCA security of pi bar. So we combine these techniques and we again use then the difference lemma. That's as in the proof of theorem 10.18. Okay? I don't want to go into the details, but that's basically what we do there. Okay, the interesting thing about, so the sort of, if you go back to this construction and we want to have this pi bar, which is CCA secure, recall how we obtained CCA security for private key encryption scheme. We use this authenticated encryption. We use the encrypt then authenticate techniques, right? So we used the private key encryption scheme that was CPA secure, and we used these message authentication codes. Yeah. To get this here to be also CCA secure. So the interesting thing about, and the clever thing about this Fujisaka-Okamoto transformation, it uses a much cleverer way to combine these things, and then it gets away with pi bar being eavesdropping secure. So we could use something that's rather mildly secure, but combine it with the trapdoor permutation and you get something that's really, really secure, CCA secure. But for that you have to use actually not just one random oracle, you have to do 2 independent random oracles to make this work. One more remark before we go into the break is all these constructions basically have the same idea, abstract idea in the back, and that is start with something that's CPA secure, modify it in such a way that decryption queries are useless. Decryption queries being useless, basically you have to modify the construction in such a way that ciphertexts have a very special structure, and to construct a valid ciphertext you basically have to know the plaintext, the message underlying it. Otherwise you will not be able to construct something that has the right format. And so in that sense, answering decryption queries always with reject, 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 as we did in the encrypt then authenticate scheme is the usual, is correct, right, with high probability. But you have to modify them in such a way, and it's really complicated. Turns out to be much more complicated in the public key setting. One thing that does not work, and obviously does not work, you should think about it maybe for 2 minutes. You may think, well, wow, in the private key setting we combine private key encryption scheme with message authentication codes. Why not using in the public key setting public key encryption scheme with a digital signature scheme? Because we always said that digital signatures are the equivalent of message authentication codes in the public key setting. You should think about it for like 5 minutes to realize that this does not work at all, no matter what kind of encryption scheme and digital signature you have, for very, very stupid reasons. So don't be clever. It's just that formally it's just nonsense. Okay. Okay, so we now go to the break, and then I'll go to the last real topic in this course, namely I go to hybrid encryption, which is the way we use public encryption schemes in practice, basically. And hybrid encryption it's called hybrid. It looks like it's a hybrid between public and private. Yes, it's the hybrid between public and private, but formally it's a public encryption scheme, but very efficient ones, much more efficient than anything that started out from our original constructions of public key encryption schemes. Okay, let's do a 15-minute break and start at 9:40. Yeah. It's 17-minute break, but anyway. Okay, good. See you then. with the last topic of this course and this section in the course, namely hybrid encryption, which in some sense picks up this, to some extent, this construction here, where we, to improve the efficiency of our trapdoor plus hardcore predicate construction, we used, in fact, a combination of trapdoor permutation with the private key encryption scheme. But we also had to use this random oracle stuff. So the question is, can we not make this a little bit easier, cleaner, where we don't go through trapdoors and random oracles and stuff, but just combine public key encryption schemes and secret and public and private key encryption schemes. And if you go back here, what's the purpose of this whole construction is, in some sense, we use a private key encryption scheme with the key K, but we hide the key K from adversaries, right, by using it basically in this Y, but then we had to use these functions HI, which we modeled as a random oracle. And we hide it only from adversaries. The recipient can actually recover it, right? Because he can, given Y, he can first recover X, and then he can apply this thing directly to recover the key. And then we use that key simply to encrypt or decrypt using the private key encryption scheme. And the question that we want to address now is, can we do that not in a more direct way, but just saying, well, okay, let's pick a public key encryption scheme to hide the key and then get a very efficient scheme. And that is really what we can achieve. Then we combine the advantages of private and public key encryption schemes. The private key encryption scheme, they are very efficient. The disadvantage is we need shared private key, and we need to rely on a key distribution or key agreement to do that. On the other hand, public key encryption has no need for shared private key, but it's much less efficient. So we want to see whether we can combine these two things, and that leads to hybrid encryption, which is a particular kind of public key encryption scheme that combines the two things and avoids the disadvantages of both of them. Okay? And this is what we want to look at. And here's directly, let's go to the construction. And if you remember this previous construction, 10.15, I think it was, then you will see many similarities. So let pi pub be a public key encryption scheme, and pi private be a private key encryption scheme. And now we define a new public key encryption scheme, the hybrid scheme, as follows. The key generation on the hybrid scheme is simply the key generation algorithm of the public key encryption scheme. So it's really, the hybrid is a public key encryption scheme. So we pick this secret key and public key. Now the encryption in the hybrid scheme on input 1 to the n, a public key and a message M. We choose first a key using the private key encryption scheme. Then we compute C1 as the encryption of the private key of the key K under the public key of the public key encryption scheme. And we compute C2 as the encryption of M, our message that we want to encrypt, under the key K in the private key encryption scheme. And our ciphertext is simply C1 and C2. Okay? So you see that we use a similar construction as in construction 10.15. We use a private key encryption scheme to really encrypt the message. But before we use random oracle and trapdoor to sort of get to the private key that we are going to use, here we pick it and generate it correctly as in the private key encryption scheme, but we hide it using the public key encryption scheme and not doing this trapdoor permutation and random oracle stuff. Yeah. The decryption, quite easy, obviously. You get C1, C2. First, you can use C1 and the decryption algorithm of the public key encryption scheme because you have the secret key to recover the key K. And then you just decrypt it using the private key encryption scheme. Yeah. And you output the result. Okay. Construction clear? And so, and what we want to prove is that this scheme, the hybrid scheme, is CPA secure if the public key encryption scheme is CPA secure, and the private key encryption scheme only needs to be eavesdropping secure. That's sort of similar again to construction 10.15, where also there the private key encryption scheme only needed to be eavesdropping secure, but the trapdoor and stuff that we can use, we were able to use to construct a public key encryption scheme. Okay? So we only talk about CPA security here. If you have here CCA security for the PIPUB and also CCA security for the private key encryption scheme, you actually get CCA security. But I will only talk about this way of the CPA security. But if you strengthen the properties of the two ingredients, you actually get a stronger, secure hybrid form of it. Okay. And as before, and this was actually the way we defined them anyway, we always assume that the private key encryption scheme on input 1 to the n outputs keys of length n. That's 0, picked uniformly at random, from 0 point n. Okay, so let's go to the proof. And before I do that, I will do something, a very general argument. It's a reformulation, basically, of our security properties or advantages, which is often used in, many people actually use them in various contexts. Depends a little bit on the context, which way you use of defining these advantages. So first we do a general observation. And I just do that in the context of eavesdropping security for public key encryption schemes, but the same thing can be done for all kinds of other variants. Public CPA security, CCA security, public key, private key encryption schemes. So let's look at the eavesdropping advantage of some algorithm, adversary A against a public pi is a public key encryption scheme. Well, just write down the definition. This is a probability for public key eavesdropping A pi of n is 1 minus 1/2 in absolute value, right? That's just our definition. Okay. How can we rewrite this? So let's look at this term here. When does an adversary in the public key setting of the eavesdropping game win? So the wins, so this is a probability that A on an encryption under public key of message MB output 0 and B is 0. Right? That's one way to win. he gets an encryption of MB. He outputs 0, and B was 0. The other way, obviously, is that he got the encryption under PK of MB and he outputs 1, and B is 1. Minus 1/2. Okay. These are the two ways in which he can win. He outputs 0 on getting the ciphertext, and the bit was 0. He outputs 1, and the bit was 1. Now use conditional probabilities to do that. So that's the probability of A gets encryption under PK MB output 0. Condition B is 0 times the probability that B is 0 plus, and then I'll just here is a bracket missing, plus the probability that A gets encryption under PK and B outputs 1. Conditioned B is 1 times the probability B is 1, and this whole thing minus 1/2 in absolute value. Right? Just these things here obviously are 1/2. And if this condition, then I can just write here M0, right? Condition that B is equal to 0, he gets M0, the encryption of M0. So what we can do here is, and I want to keep this here. So this now slides up there, and I'll keep doing things. So this here now is, I pull out the 1/2, and I will replace this 1/2 here by minus 1. Yeah? So then I have simply here the probability that A on getting encryption under PK of M0 output 0 plus the probability A on input encryption under PK of M1 outputs 1 minus 1. Yeah? Okay? Just because it's here I condition now on B being 0. So here I condition on B being 0, so I'll just write down M0. Here I condition on M1 and B being 1, so I'll just write down M1. Okay? And so now we can erase this here. Can I erase this? And the 1 gets here because I put out the 1/2 to the very front. Okay, and now we do the following. This is 1/2. This here I can write as 1 minus the probability that A on encryption of getting M0 is 1. Because this is the converse probability. 1 minus this here, and then I do plus probability A encryption under PK of M1 outputs 1 minus 1. Yeah? Then I can just these cancel. I take the absolute value, so I can actually switch the order of these two things. Doesn't really matter. So this is 1/2 probability A on input, the encryption under pk of M0 outputs 1 minus the probability A on input, the encryption of M1 outputs 1. Okay. No. Okay. In many papers, textbooks, you will find this here without the 1/2 to be directly the definition of the eavesdropping advantage. No? Without this 1/2 in front. The two things, the two definitions are just related by a factor of exactly 2. All I did was equalities. So it's really equivalent definition. And you can see that nowhere in this thing I used that I'm talking about a public key encryption scheme. Nowhere did I use that I'm talking about eavesdropping security. I could have done the same with private key and CPA security and CCA security. So this observation here works for anything. I can put CPA, CCA, private key, public key, whatever. It's always true. Yeah? Turns out that this is for the proof of the hybrid encryption, that's actually the much nicer formulation. So you should, it's always like, if you have to prove something, sometimes the original one is nicer, sometimes this is nicer. If you have some experience, you often see directly which one you should choose. Okay, so I'll use that not just for the eavesdropping and public, but also for other combinations of games and encryption schemes. Okay, so here's the outline of the proof that I'll do. I kind of do a hybrid argument, but actually in the formal proof, it's going to be a little bit different. But on a intuitive level, it's nice to imagine it as a hybrid. So let's look at the following pairs of distributions. In each of I will have 3 different pairs. It's always a pair. So in the first pair, my first element consists of public keys that were generated by the key generation algorithm of the public key encryption scheme. Yeah? Then I encrypt this scheme with this public key, and for a key chosen uniformly at random for the private key encryption scheme, I encrypt this key, K. And then I use this K, as in the hybrid encryption, to encrypt a message M0, where message M0 is the first of 2 messages that are output by an adversary A against the hybrid encryption scheme. Yeah? So the hybrid encryption, if you look at the CPA game, in the first step, then adversary A would output 2 messages, M0 and M1. I run A, I get this M0, M1, I just use M1. Yeah? So that's the first element of the pair. In the second element of the pair, I keep this here. I also keep the K here, the key in here. But here in the middle component, I encrypt 0 to the n. I encrypt a different key, not the one that I use here. Yeah? Recall that I assume that on input 1 to the n, these things always get keys of length n. So at least these two things have the same length. Okay? Okay? In my second pair, I do the same thing, except instead of using M0 here, I use the second message from the pair that A computes. And I use here, already in the first pair, I use 0 to the n. And in the second element of the pair, I use this k that was chosen uniformly at random from this here. So the difference between this and this is I just switched the order, and instead of M0, I work with M1. Huh? And the third one is I use here M0, I use here M1. In both cases, I use a key generated with the key generation algorithm of the private key encryption scheme, but here I give you 0 to the n, the encryption of 0 to the n. Okay? Okay. Now, the idea of the proof is we show that, and in the formal proof, it's basically this argument I formulated slightly differently. Here, you see that the components of the two elements of the pairs are the same except here. Right? But if this thing here, this public key encryption scheme, is CPA secure, then you should not be able to tell apart whether I encrypted k or 0 to the n. Right? So the two distributions should be roughly, for A, it should be the same. Or if I give it to a later or something else, should get the same thing. Right? Same here. It gets encryptions of M1 and M1, so they are even the same. Here it's the same. And here they only differ in this encryption of key k or key 0 to the n. But if the public key encryption scheme is CPA secure, an adversary should not be able to tell which one, whether you got something from here or here. Huh? Here, kind of the same that we did in the random oracle CPA CCA construction. In this component, the adversary gets no information about the key that I use actually here. Right? It's really no information because it's 0 to the n, and that's not. Well, k may be by accident be 0 to the n, but who cares? So, and then if I were able to distinguish between these two things, then I must be able to distinguish between encryptions of M0 and M1, where M0 and M1 are chosen by A, as in its first step. But so distinguishing here violates the CPA security of the public key encryption scheme. This violates the security of the public key encryption scheme. This here violates the eavesdropping security of the private key encryption scheme because I get no information about the key. Right? But then you can use simply triangle inequality to get that these two probabilities must be almost the same. Right? And I will explain this in more detail next, how this goes about. Okay? But that's sort of the idea behind the whole proof. Okay, so let's make this more formal. But keep this in mind. So we want to prove theorem 10 point. So let A be a fixed but arbitrary adversary against our hybrid scheme. And I denote by epsilon n the eavesdropping advantage of A against pi hybrid on input n. Okay? And let's write this down. And we need to prove that this is negligible, right? So 1 is negligible. Okay. So let's write this down. And I use my reformulation of this eavesdropping security from the previous observation. Okay. So how can we get this? So this is 1/2 this here, and now the probability that A on input with a public key in the hybrid scheme gets an encryption of M0, outputs 1, minus the probability that A on input an encryption public key hybrid of M1 outputs 1. Yeah. Just let us write down what these encryptions are, just using the definition of the hybrid scheme. So this is 1/2. The probability A gets at input the encryption under the public key of pk of k, and it gets the encryption under the key k and the private key, the message M0. Huh? Okay? Because this is just the way this encryption here is defined, right? Where keys are chosen as in the games, right? The public key is by the public key encryption scheme generator, key generator, and the private key by the private key encryption scheme generator. And here, I get this here, and then here I get the encryption of M1. Okay? Now I squeeze in several other things and apply triangle inequality. Okay? And from now on, I don't want to write out everything all the time. So I'll just write down here K, M0, K, M1, or other things. Okay? Maybe in the first thing I do this, write it out completely, but then I just put in where I change things. Okay, and everything as I need here. Forget it. So we're not going to do the horror film version here. So this is less than, because I will have used triangle inequality 1/2, will be in front of everything. Okay? Here I now write the probability A gets encryption in the public key scheme pub of K. As the first component, it gets in the private key setting M0. The is 1 minus probability A. This is the first term that we had at the bottom of the board previously. Okay. Now it will include something else, and I will do here, and here I just put in 0 to the n. Okay. Instead of encrypting key k, I encrypt 0 to the n. And here, comma, and then here I do M0 state. Okay. Plus 1/2. And you should notice this is exactly related to this here, right? At the pk, I encrypt k, I encrypt M0, I encrypt 0 to the n, I encrypt M0. And in each case, the adversary also knows pk, right? That's why I include this in these triples, I include pk. But these are just the terms that I give to A as well. But he has also pk as by the definition of our game. Okay. Now I do here the following. I keep this part here, so probability A 0 to the n, but here I do M1. Okay. Minus probability A, and now it gets here 0 to the n stays. Did I do this? What? Well, sorry, oops. Here it's still M0. Okay? It's the same from here, above here. They would cancel if I ignore the absolute values. But now I replace this here by the encryption of M1. Okay? Okay, so if you would ignore these absolute values, then this term and this term will cancel. And plus 1/2, and the probability now A. Now I'll use this guy here in the first term. So here it's 0 to the n, and here I use M1. And I subtract now the probability A, and that, let me write this down completely. Probability A on input enc pub pk of K, comma, enc K private key of M1 is 1. Yeah? Okay. So if you ignore the absolute values, then this and this cancels, and what stays is this and this, which, as we know, is exactly the eavesdropping security, and in between we use the triangle inequality. Huh? Okay? So this part here I call 1, this part here I call 2, and this part here I call 3. Yeah?
So I assume on the second part, after the minus, what's called in English, Betragstrich.
Yeah. Oh, sorry, this is wrong. Yeah, yeah, thank you. This is not there. So, and now, as I said, if we can show that all 3 terms here are negligible, we are done. Right? 3 times negligible, and we are done. Okay? So and this is really exactly what I said here, right? We would expect that this is negligible because these things we should not be able to distinguish, these things we should not be able to distinguish, these things we should not be able to distinguish. Let's make this more precise by using our assumptions on the public and private key encryption schemes that we have. Okay? So, and to do that, I look at the first term there, and I will give you an adversary against the public key encryption scheme that has exactly this term as its advantage. Okay? Why is it against the public key encryption scheme? There's nothing for the private key encryption scheme to do because it gets the same message, right? Okay, so here is our adversary for case 1 for this first thing. So let A hype be an adversary. Here on the slides I used it A hype, but which is just A here, right? I didn't want to write down all these things. Okay? So A is equal to A hybrid. So, and from A hybrid I construct this A1, which gets as input 1 to the n and pk, right? It's against the eavesdropping game against the public key encryption scheme. So it gets from the challenger this public key correctly generated with the key generation algorithm. And that's exactly how we do this since the key generation algorithm of the hybrid scheme and the public key is all generated correctly. So now A1 on input 1 to the n and this public key chooses the key k, little k itself. It sets M0 to be k and M1 to be 0 to the n. And it returns M0 and 1 to its challenger to obtain a challenge ciphertext C1, right? Which is only an encryption of either this one or this one, right? Now, upon receiving C1, we run a hybrid on input 1 to the n and pk to obtain 2 messages M0 prime, and 1 prime. Yeah? And we compute the ciphertext, now C2, as the encryption of M0 prime using the key K that we picked ourselves, that we know, and we can do that. And now we run a hype with the challenge ciphertext C1, C2. So the only difference is that here I should put a prime in there, right? It's prime. Okay? And we output the bit that I hype returns, hybrid returns. So we extend the challenge ciphertext that we get from our challenger, which only gives us challenge ciphertext for the public key encryption scheme. We extend that ourselves with all the material that we constructed ourselves to a ciphertext against a hybrid scheme. That is now, the ciphertext is really the way we expect it to be here in the hybrid scheme, and then we just output the same bit. Right? Okay. And what you can easily see then, and let me write this down. Can I erase all this, okay? And then we'll see how we get to the proof. So we just want to do this first term. Now what's we need to analyze what is the, and I call that delta 1 of n. I call this the eavesdropping advantage of A1 against pi pub on input n. Huh? Okay? Good. And by definition, this is 1/2, and I use now this my original definition, right? This is the same as the probability that A1 on input enc pk pub of M0, which is k, is 1. Right? My M0 here is this here. Minus the probability that A1 on input pk pub on input M1, which is 0 to the n, outputs 1. Right? Okay? But we know what its output is. This here, it outputs 1 if the hybrid adversary extended with this M0 prime outputs 1, here and there. Right? So this is exactly the probability that a hybrid, which I called A, on input enc pk pub of k and enc k in the private scheme M0 prime outputs 1 minus the probability that A on input enc pk pub 0 to the n, comma enc k in the private case M0 prime outputs 1. That's by definition. And all the things are generated as in the game for the hybrid attacker. Right? So this is 1. Yeah. And we know that this must be negligible because the public key encryption scheme is CPA secure. Yeah. Okay. For the third term, so we called it here 2, we can do the same thing. We reverse the order of M0 and M1, and instead of using M0 from the M0 prime from the pair that the hybrid attacker adversary generates, we use M1 star. So, and then we have the same, so the same argument for this delta 2, which I define as above, which is delta 2 of n and eavesdropping advantage of A2 against pi pub of n. Okay. So this is true for delta 1 and delta 2. Okay. Now we need an argument for our last term, where we had this 0 to the n, 0 to the n, and we had the encryptions of M0, M1 under a key K. And this is our adversary A prime. Again, we have this adversary against the hybrid scheme, and now we define A prime with challenger C against the eavesdropping security game against the private key encryption scheme. And eavesdropping here is good enough. Now we reverse the role of the public and the private key encryption scheme. Before, in the cases 1 and 2, the adversary generated the private key encryption scheme material on its own and used the other stuff for the public from its challenger. Now we reverse it. Okay? So A prime on input 1 to the n. It chooses now the secret and public key material for the public key encryption scheme itself, using the right key generation algorithm. Then we run a hybrid on input 1 to the n and pk, which we generated ourselves, to obtain messages M0 and M1. We give M0 and M1 to our challenger in the eavesdropping security game. No encryption queries. So it's really an eavesdropping game. No encryption queries to C. We return M0 and M1 to C to obtain ciphertext C2. We compute as C1 the encryption of 0 to the n under the public key of our public key encryption scheme. And now extend the ciphertext C2 by this C1 to obtain the ciphertext C. And we run our hybrid adversary on this combined ciphertext, which has exactly the distribution as in the hybrid, the CPA or eavesdropping game for pi hybrid. Okay? Everything is generated exactly as we want. And we output the bit that a hybrid outputs. Okay. Same argument, little bit different notation. Well, you have to, replace things by the corresponding things, but you get immediately that the eavesdropping advantage here, which is exactly our term from the triangle inequality thing that we got. It's exactly the third term that's still missing. And it's, again, by assumption on our eavesdropping on the eavesdropping security of the private key encryption scheme, it's negligible as well. Which shows that in our epsilon n, we have epsilon n can be upper bounded by the sum of 3 negligible functions, hence it's negligible. And that's it. Okay? Okay, so this is how we prove all these things. And you see that really the intuition is really here, right? Because this is A1, this is A2, this is A prime, what we did there. And we really use this thing there. Yep. Good, so the hybrid scheme is secure. Okay. And as I said, you can extend that to this thing where we want CCA security. Okay. Okay. Questions? There is one important remark concerning practice, which is that if you look at this here, when do we use the public key encryption scheme? The important thing is that in the public key encryption scheme is only used to encrypt messages that are not under the control of the adversary. Because in each encryption, we just encrypt a random key, right? Okay? And that's not under the control of the adversary. So it seems like, and that leads to the observation that we may want to relax our security definition. In the security definition for a public key encryption scheme, the adversary has full control over the messages that he encrypts. Here, he doesn't have that control. It's always random. And so we would like to can modify that to get a slightly weaker security definition and actually do that here also in the construction, construct the CPA thing so that you really encrypt just random messages, random bit strings. And that leads to the important concept of so-called key encapsulation mechanisms. So instead of using here a really full-fledged public key encryption scheme, in practice you do this more specialized key encapsulation mechanisms, which take into account that you just encrypt random stuff and then you can pick the random stuff together with sort of, you know the random stuff, and then you can also improve on the encryption a little bit. So that leads to the key encapsulation mechanisms that you will usually see in practice. But the proofs stay the same. It's just that you take all these things into account. And then often you will also see that they do not call these things private key encryption schemes. They call them the data encapsulation mechanisms. So you have a CAM and a DEM, a key encapsulation mechanism and a data encapsulation mechanism, and they together form this encapsulation, which is an encryption. Okay, and yeah. That's it for this hybrid encryption. Questions about this or the proof? And public key encryption schemes in practice are either used for key agreement, key distribution, or in this hybrid form. If you ever work in a company and people want to use public key encryption directly on huge messages, no, don't do that. It's not the way you should do it. Okay, that finishes the content for today's lecture and for the course. So next week I will give a brief summary of the course, and then I will also present representative questions that I typically ask in exams. These are just examples, and it's not like I pick all of them in every exam, but every exam is a little bit different. Okay. So you will have also then, you will get the chance to ask questions. What kind of answers I expect there, what kind of level of detail I expect there. And since that will only take roughly an hour or so, I suggest that we start at 9:15 next week, if everybody's fine with that. Okay, if you don't have any questions concerning today's course, then that's it for today. Thank you.